Now I hand over the mic to the chair, madam.
Thank you. Good afternoon, everybody. For the presenter's information, I would like to say one thing, that the presentation is going to be for 5 minutes and there will be a warning bell. Followed by that, the questions will be from the juries. And I request all the audience to keep silence. The juries are allowed only to ask questions, and the interactions can be had at the end during the tea session. And now, the first presenter is Mr. Munish Ratan. I invite him to present a paper on the title Array Pattern Failure Correction Using Simulated Annealing.
Very good afternoon to all present. The paper is entitled as Array Pattern Failure Correction Using Simulated Annealing. Here in this work I present how simulated annealing technique, optimization technique is used for the correction of the array pattern which has been failed due to some failure in the array. As you know, antenna array is one of the SA is a random search technique which has been actively applied to several problems in electromagnetics and wireless applications. Previously, also it has been applied for the array failure correction. For 6 to 9% failure has been considered, but we have failed more number of elements and tried it for the same problem. Plus, we have used only amplitude only control, whereas in the previous work there was both amplitude and phase controls. We have shifted to only amplitude control because in amplitude only control, only attenuators have to be adjusted. This is problem formulation. Basically what happens is, this is simple array factor equations. This array factor equation has been implemented in MATLAB, and then these are the weights. If any element is properly working, this weight is non-zero. But if the element we have to consider, if some element has failed, so then we consider this weight as 0. Suppose let's say the third element in the array has failed, so then we take W3 as 0. So this is simply showing the geometry of the linear antenna array. Then this is steering vector linear antenna array. So to point out the beam in a particular direction. Now the objective of this work is to restore the side lobe level of the original pattern and obtain the optimized directivity of the antenna array. For this purpose, a template on the basis of specified side lobe level and required shape of main beam has been constructed. Basically, this is how the fitness function has been written. A template cast is there, which has been mapped to the array radiation pattern, and difference has been calculated, and then it has been used as a fitness. Now, simulated annealing is it is a global optimization technique, and in this technique, as in the other techniques, best solutions are accepted. Here also best solutions are accepted, but here the worst solutions, they are also accepted, but with certain probability. This is the probability with which certain worst solutions can be accepted. Then essay details. These are the simulation results. Consider 32 element linear antenna array. For example, classic Dolch-Chebyshev linear antenna is used with a side lobe level of minus 35 decibel. Simulation of 6 element failure condition has been considered with the location of defective element. Let us say it is 32, so then in second, fifth, 6, 27, 28 and 31 positions. So, so this is original pattern, this is failed due to the failure of these elements. So W2, W5 and W6, W27 and W28 they have been changed to 0, and then we get this type of failure. So this is the failed pattern, whereas this is the original required pattern, and then after correcting, so we have got this type of pattern. So this is means these failed elements, these are not replaced, but the other remaining elements, their amplitude is changed, so that now you can say you get a corrected pattern. So this is the original, which was originally after failure this one pattern, and then this is the corrected one. So when the elements fail, the side lobe level increase to unacceptable value of minus 21.64 dB, as shown in the figure. This figure, this is the side lobe level. It has increased, and now it has been reduced to, it has been limited. Corrected far field array pattern is mainly which corrected side lobe level from this to minus 32 dB, minus 32.76 dB we have achieved. Initial temperature of these, this is 10, and temperature reduction factor is 0.5. These are SA parameter. Simulated annealing, we have to select certain temperature, and then it has to be cooled depending upon the temperature reduction factor. The beam width of original and corrected patterns have also been observed. So these are the results: original, damage, corrected, and in tabular form weights have been calculated. You can see the zeros for the faulty and corrected one. These are the corrected weights. Then conclusion: the array large serial of large element can be in some certain applications it may not be possible to replace the elements, so we have to correct. These are the references.
I would like to know the utility of this research, in the sense that you already know what are the elements have failed. Okay. Secondly, even if you are trying to correct with the amplitudes of the other elements, you are not getting the same beam width.
Not
For
exactly
4.2 degree and 6.1 degree.
Exactly same beam width cannot be achieved. There will be certain error if you see, if you consider large number of failure elements, more elements have failed, so then we cannot reproduce the complete original pattern which was possible without failure of all the elements. Like in certain applications like defense space applications, we cannot replace the element, but we can. Yes. Okay. So, okay. Yes, yes. Yes. This is the question, because this work is focused on only on array correction. The title of the paper is also array correction. So I am not detecting the elements. Failure detection is not the part of this work. So there can be one failure detection technique also, that is how to detect the failure elements, and then it can be corrected. But here in this work, it is assumed that we know that which elements have failed, and then it is corrected. It is the assumption that these elements have failed, and then it is not correcting to the extent to the expectation of the sir. It is well possible.
Thank you.
Shall I ask one question?
Uh,
I have.
Should I?
we are running shortage of time. Uh,
We did similar work in our university failure back in 2004, and that was encompassed both failure detection and correction. I've got the results here. Correction was very nice. I mean, reading was this discrepancy, one of them, our techniques were absolutely different. The detection was using GA, and at that time other evolutionary algorithms were not as developed.
Sir, what was your failure rate?
Yeah, that was we checked up to. I'm telling you, I've got all the results. I'll just
excuse me. We shall have such a discussion afterwards. Thank
but
you,
anyway, you can
Rajan.
get this in International Journal of Electronics in 2004. I just want to give you the reference in May.
I would like to
It was
thank
much
Rajan.
bigger, right?
The next candidate to present the paper is on the title Trapezoidal Tooth Log Periodic Antenna with Microstrip to Coplanar Stripline Transition. I request Situ Rani Patre to present.
Very good afternoon to everyone. My name is Seetu Rani Patre from IIT BHU Varanasi, doing PhD under the supervision of Professor S-2. My topic of the presentation is trapezoidal tooth log periodic antenna with microstrip to coplanar stripline transition. The objective of this work can be divided into the two parts, that the simulation design and the simulation study of trapezoidal tooth log periodic antenna, which is a balanced type of the antenna fed through a microstrip to coplanar stripline transition, which is a balanced type of the feed. After this simulation, I've observed the effect of this microstrip to coplanar stripline transition on impedance bandwidth and the radiation pattern of the antenna. Introduction. In the recent year, high-speed wireless communication has been grown enormously. So this high-speed wireless communication requires wider bandwidth of the elements constituting communication link. This requires the broadband antennas. So I have considered the trapezoidal tooth log periodic antenna developed by Duhamel, which belongs to the family of frequency independent antenna. While designing this antenna, I found one of the problem that it is a balanced type of the antenna. So for the proper feed, it requires a balanced type of the feed along with the impedance matching. So after some study, I found that the solution is the balloon. Balloon is a transition between the unbalanced feed line and the balanced antenna, or vice versa. So for the proper connection of the antenna to the coaxial cable, the balloon is designed in such a manner that impedance matching should be there and field transition over the operating frequency band. That consider this microstrip to coplanar stripline transition. Here it consists of the two sections, that is the impedance matching section, which has a tapered version of Chebyshev 3-section impedance transformer to transform the impedance from 50 ohm to 200 ohm. And another section is the radial stub here, which is a quarter wavelength long at 2.6 gigahertz, which is the center frequency of the antenna. At 2.6 gigahertz, I have plotted the surface current distribution. Here you can see at 2.6 gigahertz, the current has the approximately equal magnitude at the CPS and the currents are opposite in the direction. Now this transition is connected vertically to this antenna, trapezoidal tooth log periodic antenna. This antenna has been taken from one of the reference, and the frequency range is 0.588 to 4.7 gigahertz. The longest tooth is quarter wavelength long at the lowest operating frequency, and the remaining teeth are decided by these two equations. The design parameters of the transition and the antenna is shown in this table. The novelty, I can say that the tapered version of Chebyshev 3-section transformer design and the vertical connection of the antenna and the microstrip to CPS transition. After that, the effect of this radial stub is shown here on the radiation pattern of the antenna. The simulation results. Here you can see the reflection coefficient variation with the frequency. From this plot, we can see that the reflection coefficient is less than minus 10 dB for the frequency range of 0.6 to 4.2 gigahertz. That is the bandwidth of 7:1. We can say that here there is a well impedance matching between the coaxial antenna and the coaxial cable feed, which is mainly due to the tapered microstrip line. Another result is the surface current distribution at different frequencies. Here we can see that the smaller teeth are resonating elements at higher frequencies, and approximately identical current distribution on both the arms of the antenna at 2.6 gigahertz. And as the frequency changes, the current distribution changes in the two arms. The radiation pattern at 2.6 gigahertz, the radiation pattern of the antenna in the vertical plane is bidirectional. But as we change the frequency, the radiation pattern gets distorted. And the peak realized gain varies from 2.2 to 8 dB in the operating frequency region. The conclusion can say the trapezoidal tooth log periodic antenna with modified tapered version of the microstrip to covalent strip line transition has been presented, and this microstrip to covalent strip line transition is responsible for the impedance matching and the field transition. That is, the bidirectional pattern is obtained at 2.6 gigahertz. The input reflection coefficient is less than minus 10 dB from 0.6 to 4.2 gigahertz. That is the bandwidth of 7:1.
You can finish off. It's already time.
Bidirectional radiation pattern at 2.6 gigahertz, which is the design frequency of the balloon also. Peak realized gain 2.2 to 8 dB, and this may find numerous application in communication, navigation, surveillance, broadcast. These are the references I have used.
I request you be prepared for the questions from the jury.
Okay, in this paper, your main contribution seems to about this transition design. Okay.
Yes.
And it seems you didn't test your transition. Did you?
I have tasted in simulation only.
You should have tested your transition first.
Yes.
How do you know that it gives a 180-degree phase difference between the two arms over the whole frequency band? Over you're talking about something like 0.5 gigahertz to 2.6 gigahertz or so. How do you know that it has the really working, having the proper phase difference over this whole frequency band?
No, it is not giving the proper phase difference in the whole frequency band. At 2.6 gigahertz, here we can see the current distribution is...
Try to cover a smaller portion in depth. I think that is the basics of research. Don't try to cover too much. With
that is the problem I am facing.
Yeah.
So, if anyone knows, I'll be grateful to please know the answer.
Okay. Thank you, Sithu Rani. The next paper on snake prey algorithm for calculating resonant frequency of rectangular microstrip antenna. I request Sastri Golapudi to come and present.
respected Dr. Patnaik sir, session chairs, juries, and learned dignitaries, and dear friends, all of you, good afternoon. Today, we are going to launch a new algorithm which was not at all existed in the universe, called as snake prey algorithm, which was applied in the application of rectangular microstrip patch antenna for calculation of resonant frequency. So in these are the others, myself, Dr. Vidyasagar, and one of my friend, Mr. Sai Galapudi, and he is a field engineer in Airtel Corporation. The objective of this one is finding of resonant frequency of rectangular microstrip patch antenna. The rectangular microstrip patch antenna, all of you knows that. The figure was shown over here. Next. Next. The design and design parameters are the most essential for this. Here, it is a soft computing or a soft fusion technique of SPOT and BFOA. The SPOT is nothing but snake prey optimization technique, which was innovated and delivered by these authors with the motivation and guidance of Dr. S.S. Patnaik, and it was already announced and established in 2008 advice. And now it was hybridized with bacterial foraging algorithm, which was pronounced like a local explorative compared to PSO, which is very prominent. Now all the researchers are using of that one. So first of all, let me have a brief interview or discussion about the SPOT. So I think some of the people might have known, some of the are unknown of that fact. The SPOT is nothing but snake prey optimization technique, which is residing in Amazon River in US. So it is different from other snakes. It is also called as buffalo snake. It is mainly having of a feature having of sensory levels. In general, any prey has to be caught by the hunter or chaser or predator till the prey, whenever the prey will be there, the chaser has to go over there, predator should go over there and catch it. But here, the snake will not go anywhere. That is the difference of ordinary snake and buffalo snake. Here, how it will catch the prey. Here, what the snake will does is, whenever the prey is there, until and unless it will comes into the arena of snake, it won't move at all. It is a consisting of sensory levels. When the sensory level is continuously increases, it is having of a thought that prey is nearer to me. Once the prey is very nearer, its sensory levels are too high and making of the prey to be catch. So mimicking of this buffalo snake nature, we were implemented the software code called as soft snake prey optimization technique. So why we should introduce this novel technique is, the reason behind of that one is, in other cases, we are always in search, either in PSO or BFO or in other bio-inspiring algorithms. We are having a number of parameters, and the people who are too new to this research field has to study more. So our motivation, the SAR was told that whatever the existing algorithms are not meeting the required challenges. So what we have to do is, it must be innovative unless the prey should come over, the actual value should not come over, your algorithm should not work at all. So making of that into conclusion, so what we are doing is, we are combining our SPOT and BFOA. In BFOA, we are having of reproduction, elimination, swimming, tumbling. So we are removing of all those things. We are using of only swimming and tumbling. Since there is only one prey, there is no reproduction, and there is only one operator. That operator is called as velocity operator. So since the operators are less and the computational time is less, and hence this becomes popular. But we know that one PSO is popular for global exploration, but it is having a disadvantage of local track. For avoiding of that, BFO we are using. So combination of those two, making up this algorithm to be more robust compared to any existing algorithm of bioinspired. So this is a new technique which was modern and novel by these others, which was not at all developed anywhere. So now you will see that.
Already time is off. I request juries to raise questions.
Thank you.
I bless all of you. I need the blessings for all of you elders. This is the little child, just born child. So all of you must bless this bioengineering algorithm should evolve a new arena in the entire CAD applications.
Thank you, Mr. Sastri. I request the next presenter, Mr. Rahul Srivatsava, to present a paper on the title, A Diagonally Triangular Slotted Sierpinski Fractal Patch Antenna.
Deepika? इतने डालो ना कैमरे को
Let us move on to the next person, Mr. Lakshmanan Papula, a paper on the title Planar Thin Antenna Array Synthesis Using Multi-Objective Optimization.
Good afternoon to all. My name is Lakshman Popula. I am research scholar from IIT Bhubaneswar. My supervisor is Dr. Dublin Ghosh. Today I want to present one of my research topic on the planar thin antenna array synthesis using multi-objective optimization. Actually, in general, in nowadays, antenna arrays is widely used in communication systems, but controlling the that means that controlling the radiation pattern in terms of the lowest side lobe level is one of the main important factor in designing of any antenna array. For that, so many techniques are there to decrease the side lobe levels by using the amplitude distribution, by using the phase distribution, at the same time by using the position optimization. But while dealing with the large antenna arrays with large number of elements, by using the amplitude distribution, phase feeding complexity will be more. At that time, what we will do? We will go for a periodic antenna synthesis. A periodic antenna array synthesis also dealing with large antenna elements becomes very complexity, mechanical complexity. How many elements we have to change for every time? So at that time, we will go for the thin antenna array synthesis. That means we are using the uniform feed, but we are switching off some of the elements in order to get desired radiation pattern in terms of low side lobe levels. This is, because this has so many advantages in terms of reduction in weight, cost, and feeding complexity will also be less compared to others. So actually, see from that, this is a 40 element array radiation pattern. The main lobe is there with so many of side lobe levels. But what is the problem is that after synthesizing, after switch offing some of the elements, the radiation pattern will becomes like that. This is the blue one indicates after synthesizing. See, after decreasing the side lobe levels, what is happening between the beam width? That is increasing. That means if you decreasing more the side lobe levels, beam width will be affected. So if you increase the side lobe, beam width will be less. That means that in this case, is it necessary to develop a multi-objective optimization in dealing with the terms of the conflict parameters. We have to define some set of compromise solutions which will be useful for the antenna designer. From the set of compromise solutions, he will select based upon his application. For that, we are developing a multi-objective optimization for the thin array synthesis or to produce the compromise solutions in terms of functional beam width and the side lobe levels. Actually, this is the planar antenna array. For the actually, my problem formation is that we have to maintain the narrow beam width. At the same time, we have to maintain the low side lobe levels. For that, what are the best array configurations? We have to choose from that using the multi-objective optimization. Here, we are using. We have taken the 20 by 10 planar antenna array, that means 200 elements will exist, large planar antenna array we have taken. From that, we are choosing. This is the Pareto front using we get some of the solutions, compromise solutions, best compromise solutions in terms of PSSL and FN beam width. From the discussion, I choose one of the solution from that one. That is the corresponding array structure, which black one indicates on elements, white one indicates off elements. From that, we are controlling the shape of the radiation pattern. From that, we are comparing with that already existing technique, GA, single parameter optimization. By using single parameter optimization, we are decreasing the side lobe level, but we can't control on the functional beam width. That's why we go for multi-objective optimization. For that, in all planes, if you take the planar array, whatever the plane you take, we are maintaining here 19 decibel side lobe levels at the same time with 54% side field aperture. One of the disadvantages is there, gain is decreased because in some applications is there the satellite. If I taking the satellites, gain is the secondary there, PSL is the primary there. At that time of that type of applications, this is very useful. Here, 54 field aperture, 28 less very narrow beam width compared to already existing 147 degrees. Further with low PSL. From that, we are taking the compromise solution. Like that, this is the radiation pattern. This is the radiation pattern for in all planes. We are representing up to 0 to 90 degrees planes. At the same time, we are taking the Cartesian format at 3 different planes. We are maintaining 19 decibel side lobe levels, like that. That's why in this way, what are the conclusions? By using the multi-objective approach, we have the great control of controlling the radiation pattern in the desired level. It is very useful to the antenna designer, which will select from the Pareto front based on applications. It is very useful to in the terms of antenna array synthesis. Thank you.
Questions from juries?
So many literature has been done on this direction, right? Multi-objective optimization, GA,
Yes.
micro GA, PSOs, and improved PSO, modified PSO.
Yes, sir.
People have done it, right?
Why we are using means that so many are there, but whenever you trace for 30 trays, 50 trays, 70 trays, it has to come, robustness is required. Whenever you do, the same Pareto front will come. Best one time you come, the good solution will come, another time it come to bad solutions, it will not good. We have tried for multi-object PSO also. For every trial, we get the same Pareto front, what you are achieved here. Same Pareto front in terms of like that. Further, it is very useful for that while using the practical. It is not. It is robust. That's why.
How many objectives you are using?
2 objectives are using here.
2 objectives.
Yes, sir.
You almost any trial, whether you use this or anything else, Pareto front is not going to change.
What's that?
Pareto front is not going to change with 2 objectives. Have you taken 5, 7 objectives, more than 5? Then you can see the changes in Pareto.
If you
Two objectives.
Two objectives, see, this is one objective, this is another objective. If it three objects, three dimension will come. Here,
then only you can see the Pareto change in the Pareto front. This will not give you any changes. This will almost remain constant always.
No, sir. For every simulation I want. For every simulation, the relation between the compromised solutions we have to find.
Yes.
For every simulation, if you get the same Pareto front, then you tell that whatever the proposal for this planar thin synthesis is robust for that one.
That is what.
Yeah, that is always more or less always happen now. If you use the same computer, you will get the same result all the time.
No, sir. This is
run the same algorithm.
This problem is purely multi-model problem. So many local minimas will be there.
That is true. Now I have a question. You have a GA optimized result. You have a NSGA optimized result. Both of them are supposed to get you the global optimization.
Sir, this is GA means single parameter. Here we are using the two objectives is there. Single parameters means you got.
If you are comparing two, you will compare them.
No, this is the first method you are proposing, the planar thin antenna synthesis.
Are you saying that nobody else has done planar thin antenna?
Yes, sir. This method, planar thin antenna.
No. I asked you a question. Are you saying you are the first one to do a planar thin antenna?
Planar thin antenna array by using multi-objective approach.
Then other people have done with other approaches.
No, sir. For this synthesis, aperiodic antenna synthesis is different, thin antenna synthesis is different.
Okay. Thank you, Mr. Lakshman.
Thank you.
The next presenter is Danveer Mandal on the title FDTD based analysis of pending effects of variable patch antenna.
Good afternoon, everybody. The title of our paper is FDTD based analysis of bending effects of variable patch antenna. The objective of this paper was to write a code in FDTD to calculate the scattering parameters of variable patch antenna and then analyze the effect of bending in the variable patch antenna using FDTD. For this analysis, we have taken the antenna from the paper by Sheen. You can see the dimensions. The height of the substrate in Sheen's paper was 0.794 mm and the relative permittivity was 2.2. Since we are assuming that it is a variable patch antenna, so we kept the same height and same relative permittivity. The governing equations in FDTD you can see, and this is the coherent limit for stability. If we take the discrete equations of Maxwell, then we get 6 parameters Ex, Ey, Ez and Hx, Hy, Hz. Out of 6 I have shown 2 here, Hx and Ez. This is the modeling of bend in the antenna. We have taken last 10 cells to model the bend in the y direction and 8 cells in the z direction. We have kept the same height of the substrate. You can see the ground plane and the patch. And in this case, because the bend is passing from the cell diagonally, we can calculate the angle, which is 33.524 degrees. In this case, the delta x, delta y, delta z, you can see the computational space is 62 by 120 by 20, and Gaussian pulse is used to excite the antenna, and we have used resistive voltage source for the excitation. Novelty in this design is that we are modeling the bend by using the FDTD method, by writing a code in the MATLAB. We are not using any simulator for this. And we have used a resistive voltage source to excite the antenna. And the scattering parameter is calculated using DFT. This is a few snapshots of the simulation. This is the EZ at time steps 200. Then at 1500, you can see here a band, the effect of band. And this is the Gaussian pulse propagating through the strip line to the antenna. This is at time step 350. This is the input pulse applied when there is no bend, and then the reflected signal. The simulation was run for 4,000 time steps. Then after bend, with bend, you can see the change in the reflected signal. This is the scattering parameter that was presented by Sheen. Without bending, we have achieved the same results using FDTD. But when there is a bend, in our case, there is a significant shift in the resonant frequency. And 3 other bands were generated. So without bending, the resonant frequencies are these, and these are the scattering parameters. And after bend, this frequency shifted to 8.883 with scattering parameter minus 14.02. Similarly, this new resonant frequency is generated, and this resonant frequency, in spite of this, we have 2 resonant frequencies. So analytical result says that there is a significant shift in the resonant frequencies due to bend, and it could be because of the effective length of the antenna is changing. And in the case of bend, the convergence was achieved after 3,000 steps, whereas without bend it was after 4,000 steps. The conclusion is that we have modeled the bend in a variable patch antenna using FDTD method, and scattering parameters is calculated using FDTD and DFT. And the bending of the variable patch antenna, it causes a significant shift in the resonance frequency. In future scope, one can go for the calculation of the radiation pattern and the input impedance in case of bend, and you can also calculate the effective length of the variable patch.
Question time for the juries.
These are the references.
Is there any validation of the results you have got?
Sir, we have not done the experimental results yet.
No, even from the simulation, you have written your own code.
Yes, sir.
And then you could have used some commercial software and check about the validation.
Sir, we have checked in HFSS, but that results we have not included here.
Huh?
We have checked in HFSS.
Where are the results? Does your results match with the HFSS results?
Sir, because this same result you can have in the HFSS, but to model a bend in the HFSS is very difficult.
Why?
This type of bending.
I would say that it should be much easier over there than what you are doing.
It's at least you have tried to write your own code. That I should appreciate. But I should ask you,
you have used the conventional, cubic cell FTTD.
Yes.
And when you are doing bending, there are effects, staircasing effects.
Sir, we have not used staircase.
You have not used staircase, but your
Actually, sir, the patch is passing diagonally from the cell. So only the tangential component of the electric field, we need to set to 0.
How, which algorithm did you use?
Sorry?
Which algorithm did you use?
Sir, FDTD method.
Within that?
Because when there is a metal, the tangential component of electric field should be 0. That is how we model the
When you go to your results in the next page, next slide also, next one. Okay. Yeah, it seems like you have a sort of S11 null at DC. How will you explain that? On the bent model, second one.
This one.
At 0 frequency.
Yes, sir. I don't have any explanation for this right now. But first we will go for experimental results. Then
I have a question. Just 1 minute. See what
Thank
Sir
you.
was asking.
Thank you.
1 minute. Sir was asking that normally when you bend, you can think it's a question as well as a suggestion. When you bend, when you make the structure conformal, there are two things. The radius of curvature with wavelength you have to say. Otherwise, it doesn't have the full meaning. Once you specify that, the things have significance in terms of frequency shift. Normally, if you bend using a long antenna, your frequency shifts to higher frequency.
Later, sir,
But at the same time, your beam width will increase. But you have not projected.
Sir, we have not calculated the radiation pattern and input image. That is
Thank you, Mr. Danvir. We'll have a discussion later. The next presenter is Mr. Pradut Kumar Bharti on the title A Compact Planar Shorted Monopole Antenna for Mobile Handset Applications.
Good afternoon, all of you. Myself, P. Bharti from IIT Varanasi. Today, my presentation is a compact planar shorted monopole antenna for mobile handset applications. My objective is design antenna for mobile application, which is following specification. Today, demanded are more and more band to accommodate a single antenna. So I am designed to antenna should be operate GSM at 1500 MHz, 1900 MHz, 1800 MHz, 1900. So UMTS LT 2300 to 500 and WLAN WiMAX frequency band. Antenna should be compact, planar structure and low cost profile, and radial pattern also should be omnidirectional. Mobile evaluation today, mobile is antenna is slowly become more and more integral, and today is a very small, more functionality, also improve the performance, and also is all cell phone have E91, E911. This is emergency call facility is also capable for antenna design challenge. So today is more for design to microstrip antenna. This is low profile structure, low cost manufacture, highly integrated with PCB and multi-functional service like such as voice, video and data communication, like game, so many applications inbuilt. This is proposed antenna for multi-band application. This is choose for substrate material FR4 glass epoxy with dielectric constant 4.4 and last segment 0.018. The dimension of the PCB for mobile antenna is 50 by 110 mm, and also thickness of the substrate is 0.8 mm. This is all design are submitted to carry out with HFSS submission software and further validity by CST Micro Studio. This is optimized parameter for this is antenna for this design for this like L1, L2, whole dimension from here detail, and this is value. And for the design of the my antenna, this is this is Mendel line structure. This is designed for this band as a lambda by 4, and this band is like C-shape structure. Designed as also in lambda by 4, designed to GSM 1800 frequency band, and again to this patch is started by this strip. This length is also nearly lambda by 4 to 2.45 gigahertz. This band covered to this band. So and also this strip is add to matching equipment for the band, this band, and also this band. Means this is added to this step. Then this band is wide band for achieve to more mobile communication application. For suppose this band is 1900 megahertz to 276 megahertz, and this is also WiMAX frequency band. This is a current distribution. The surface current distribution for different frequency like 0.9 gigahertz. This is responsible by more current radiation from this portion, and also 1.9 in current distribution from radiation from this portion. So 0.9 gigahertz to design for this structure, and also 2.45 gigahertz and 3.5 gigahertz frequency. This is a radiation pattern for H plane and E plane co and class polarization for different frequency like 0.9 gigahertz, 1.9 gigahertz, 2.45 gigahertz, 3.5 gigahertz. This is a realized gain to planned by simulation software. This is for center frequency for band, all frequency to cover for mobile application. This is conclusion. Compact structure, compact planar started monopole antenna suitable for the mobile handset application is presented. This is a Mendel line structure is presented that this is for this and sorry. This is a application. This for this reference.
You have shown the surface current distribution at 4 frequencies.
Yes, sir.
And the radiation patterns over there.
Yes, sir.
Yeah, what I would like to know, can you establish the correlation between these frequencies, radiation pattern, and the modes of the antenna?
What, sir?
Modes.
Modes. Mode is a fundamental mode generate TM10 mode for 9 gigahertz and 1.9 gigahertz, and other higher mode generate from 2.45 and 3.5 gigahertz.
How do you say that this is fundamental, this is higher?
This is a fundamental mode because I am designed to suppose this is designed for this structure 900 megahertz. This band, this is fundamental one, and also design this structure CC flat in nearly 14 mm. This is lambda by 4 is one this. So this is fundamental mode for here and this structure, and also higher mode generate for.
Terms of what we call it as TMMN, like that. Then only you can say that it is this mode. You can say if you are right now you are saying fundamental mode, dominant mode, and higher order mode. But which higher order mode belongs to which particular Mn value? Can you give that?
Mn equal to
Variation along x and variation along y. Current variation.
So Tm 0 mod. So Gm at 0 1 mod 0 Mn M. Yes, sir.
Sorry, there is no question invited from audience at this time. Thank you, Mr. Prabhu.
Thank you.
The next presenter is Mr. Pushkar Mishra on the title Squares Staircase Spectral Antenna.
Okay, good afternoon to all. So my topic for presentation is square staircase spectral antenna. My name is Pushkar Mishra. The main objectives of my topic is to design a new staircase spectral antenna, to simulate the fractal antenna in our software, then to fabricate the proposed antenna, and then to analytically analyze the antenna by mathematical expressions and to compare the simulated as well as the measured results. This is the design which was designed in HFSS electromagnetic software, since as you see from the figure, the dimensions of the antenna is 20 mm by 20 mm. Now we have did these two iterations in the fractal antenna. The outermost is the first iteration, and the inner second ring in the inner structure, it is the first iteration, and the last one is the second iteration. Since as you see in the structure, from this to this is 20 mm by 20 mm, and the second structure is 10 mm by 10 mm. So the scaling factor is 1 by 2. Similarly, the third structure, which is 5 mm, the scaling factor for this structure from this structure is 1 by 2. So this is a fractal geometry. Design parameters, as we can see, we are using the FR4 substrate with thickness of 1.575 millimeter. Dielectric constant is 4.4 with loss tangent of 0.009. We are using a coaxial probe feed to feed the antenna, where the x coordinates for the feed point is 11 mm, as well as for the y coordinate it is 7 mm. Novelty in design, since the geometry is new, so first is new staircase geometry. Second is, as it is a fractal antenna, so the electrical length of the antenna is increased. So this is the novelty in this design also. And multi-frequency response, smaller size, and bandwidth is higher, as we can see from the results. These are the simulation results of the antenna. Since there are three frequencies we have got from the antenna, first is at 4.4 gigahertz, second is at 0.7 gigahertz, and third is at 10.61 gigahertz. These are the radiation patterns of the antenna. The first one is figure number 3 is the total gain of the antenna with second iteration, and figure 4 is the total directivity of the antenna, and figure 5 is the azimuth radiation pattern of the antenna. Gain of the antenna from the total figure number 3 is for 4.4 gigahertz, the gain comes out to be 1.154 dB, and for the second 7.7 gigahertz, the gain is 3.5, and for the third one, 10.61 gain is 5.83. Analytically, first of all, we have used the simple microstrip patch antenna equation to find the length of the antenna, and mathematically, for the first frequency band, effective length of the antenna comes out to be 20.9 millimeter, and actual length comes out to be 19.14. Whereas for the simulated, we have simulated the same design that it is 20 mm length, and for the fabricated, we have fabricated the design at 20 mm length. So there is a very small gap between the mathematical expression and the simulated one. This is the simulated photograph of the antenna. The figure 6 describes the experimental setup of the case factor antenna, whereas figure 7 describes the major results of the return loss or the reflection coefficient of the antenna. In major results, we get two frequencies. One is at 4.46 and another one is at 12.15. So for the second frequency, which is at 12.15, we have got in simulated 10.61. So there is a slight between the second band, and 7.7 band is not there in the measured results. This is the comparison between the different parameters. The first one is the simulated return loss, which is at three frequencies, 4.4, 7.7 and 10.61, with gain of 1.154, 3.88 and 5.57 at an angle of 0 degree, with the elevation 32 and 8, whereas azimuth angle is 0, 180 and 0 degree, with bandwidth up to 43 megahertz to 50 megahertz and 386 megahertz. The application of the antenna for 4.42 is satellite communication, can be used for downlink frequency. 7.74 can be used for ITU downlink frequency band, whereas 10.61 can be used for terrestrial band application. Second, we describe the simulated return loss and measured return loss. 4.42, we get the first frequency of 4.42, whereas for the measured, we get 4.60. Second one is not there in the measured results, and third one is 10.61 and 12.15, which is slightly mismatched. So for the this is the conclusion. And for the future scope, metamaterial loading can be done to same antenna to slightly shift the results in the measured to the 10.61. So metamaterial loading can be done, and antenna substrates such as RD dioride or different substrates can be used to utilize that frequency shift or to increase the gain. And these are the references. Thank you.
When you started this, a number of iterations, right?
Yes, sir.
You stopped with this second or third iteration? Third, huh?
No, sir, second.
Second iteration.
Second iteration.
Why it's so?
So the first one, suppose this there is no two rings inside this structure, and the first structure is the outer ring. This is the zeroth iteration. Then we put another structure. This is the first iteration. This one structure, and there is no structure. So we put again another structure inside this structure, and this is the second iteration. So it is basically a reverse fractal geometry we are using. Generally in fractal geometry, we put some metal, remove some metal from the copper patch, but we are putting some metal so that for the application based, if we want only one frequency band, this structure should not be there. This frequency band can be eliminated, and we can put some other metal or element in the PCB design. This space can be utilized.
How do you describe the difference between your measured results and the simulated results, in the sense that the dominant mode, there is hardly any difference between the two frequencies, but the higher frequency, there is a lot of difference, 10 gigahertz and 12 gigahertz, something like that?
Yes. First of all, sir, during fabrication we are using a FR4 substrate, so it is very much lossier. Secondly, when we are feeding the antenna with the coaxial feed from the bottom, air gap is there, and due to some air gap or coaxial feed, there must be some ohmic losses, due to which ohmic losses the frequency may be get shifted.
This antenna, where are you feeding?
Actually, sir, here. At this point, 11 and 7.
So you are feeding in the outer.
Yes, outer ring.
Outer ring.
Yes, sir.
And which is supposed to work at your 4 gigahertz or what?
Yes, sir.
Right? And at that frequency, you said you are getting a gain of 1 dB or something of that.
Yes, sir, 1.15.
This is a microstrip antenna, isn't it?
Yes, sir. Microstrip patch antenna.
Yeah. So how do you justify the low efficiency there?
Efficiency.
Because you are only getting 1 dB.
Sir, actually we are, since for the first 0th iteration, we are using only outer band. So to utilize that, we can use metamaterial loading over there. Since fractal antenna is having narrow band and low gain and low frequency. To utilize, to increase that gain and bandwidth, we can do metamaterial loading over there.
Thank you, Mr. Pushkar. Next, I invite Mr. Chahat Jain to present a paper on the title, A Novel Multiband Fractal Antenna on a Fractalized Mushroom Stack. She is Ms. Chahat Jain.
Respectable Chair, Jury, and dear antenna community friends, I am Chahat Jain from Guru Nanak Dev Engineering College, Ludhiana, and here I present my work entitled A Novel Multiband Fractal Antenna Design on a Fractalized Mushroom Stack. For starting this project, few things in my mind were like, first, the complexity of the structure should be less. There should be reduction in the metal, that is the cost reduction, and the same antenna could be used for more than a single operation. So, with an aim to achieve compactness to fit in the ever-shrinking technology, the objective was set as to design and analyze the performance of a low-profile fractal antenna mounted on a mushroom stack AMC, which will be acting as a very good ground plane. So first thing was to design a mushroom type AMC. It consisted of an area of 4x4 patches. The space between them, between the patch and the dielectric was filled with taconic CR10, permittivity 10. The dissipation factor was 0.0035. Thickness was 2.54 mm. So after the design of AMC, I designed a fractal antenna with the following specifications: taconic RF35, epsilon R 3.5, loss tangent 0.0018, substrate thickness 1.52. The initiator was of size 32 × 40 mm with a circle inscribed in it of radius 8 mm. The frequency of vibration I have chosen is basically 2.45, basically used for mobile, Bluetooth applications or various handheld devices. The nth iteration is basically 1/3 of the previous iteration. The novelty in the design is I have constructed an AMC without the use of wires, because I could think of the objective as reduction in the complexity of the structure, reduction in metal, that is why reduction in the cost as well. This shows the side view as well as the top view of the structure I have made. Moving on to the results, the first was the analysis of the return loss. Results is basically the comparison of between the conventional metallic conductor that we use and the other is the AMC that I'm using. The possible reasons that I could think for the improvement in these return losses is the in-phase reflection surface, and the second is the surface wave suppression at that surface of AMC. This is an improvement of 8 dB. Next was the VSWR comparison. In conventional one, it was 1.86. In the AMC, it was around 1.7. This was the analysis of directivity and frequency. This was the multiband functionality. It is operating at 4 bands, basically because of the larger radiation area within a given dimension, the fractal functionality. Conclusion, the results have been achieved for reflection coefficient of 8 dB, impedance bandwidth has been improved, directivity as well as VSW are improved, the multiband functionality has been achieved. Future scope, if we look for the immediate future applications, it can be in various microwave circuit applications. Optimization algorithms like BFO, ASO, PCO, PSO, or various other hybridized forms can be used for solving complex electromagnetic problems. If we look for very far away applications, I could find these AMC structures can be, or fractals can be used for military oriented antennas with the properties of multiband functionality and their transparent structure. The last prospect which I found very fascinating was if these corrugations are dealt in a visible electromagnetic spectrum, they could be used for invisible army, which I have studied as a future scope. These were the references that could help me pursue my work. Thank you.
Okay, just I would like to know whether you tested your AMC surface or not.
No, sir, I am a newbie in this field of metamaterials. I have just simulated.